Property 7 of the DFT is called as multiplication property. Here we are multiplying the two sequences in the time domain. It's also called as a modulation property. This results in convolution in the frequency domain. The statement goes something like this: if x1 of n is the input, its DFT is called as capital X1 of k. x2 of n yields a DFT capital X2 of k. Then the product of x1 of n into x2 of n will have a DFT which is 1 by n times the circular convolution between x1 of k and x2 of k. To prove this, let us consider the proof first. We talk about two sequences x1 of n and x2 of n, each of length capital N, with DFTs capital X1 of k and x2 of k. Now, according to the expression, here we're taking the IDFT equation. The IDFT of capital X1 of k will be equal to x1 of n, the time domain sequence. From the definition of IDFT, we can write it as 1 by n times summation L is equal to 0 to n minus 1 x1 of L times Wn to the power of minus Ln. This comes from the definition of IDFT, but we prefer to have index L for the first summation and M for the second summation rather than the regular index which is called as K. Just to distinguish between the two terms, we are using different index names. So similar lines, the IDFT of x2 of k is x2 of n given by the expression 1 by n times summation m between 0 to n minus 1 x2 of m into Wn to the power of minus mn. Let y of n describe the product x1 of n into x2 of n. Then its DFT can be denoted as y of k. From the definition of DFT, we have n between 0 to n minus 1, y of n, Wn to the power of kn. We are aware that y of n is the product of x1 of n and x2 of n. So inserting it in the equation, and later, since we have developed two equations to represent the two terms, let us replace it. So substituting the values of x1 of n and x2 of n from the above equations, this is what we get. Now here we observe that we have three twiddle factor terms which I have numbered here just for convenience as 1, 2 and 3. Now these three terms we need to simplify. We observe that 1 by n is a constant and can be taken out. So since there are two such terms, we have 1 by n square. The first summation L between 0 to n minus 1 x1 of L. The second summation m between 0 to n minus 1 x2 of m. And the third summation will have the twiddle factor terms. That is combining the powers Wn raised to k minus L minus m into n, where n is common in all the terms. Now, to perform simplification, the term k minus L minus m, let us represent it as Pn. Now, Pn here is a multiple of capital N. P is an integer, so it's an integer multiple of n. In other words, m here is nothing but k minus L minus Pn, which is same as applying mod n to k minus L. Similarly, L can be represented as k minus m minus Pn, which is k minus m mod of capital N. Then the summation, the last summation, the third summation becomes summation n is equal to 0 to n minus 1 Wn raised to k minus L minus m into n. It becomes summation n is equal to 0 to n minus 1 e power of twiddle factor in the exponential form, e power of minus j2 pi by n. This term we decided to call as Pn, so we substitute for Pn, so Pn times n. And this results in cancellation of n, and we have integer multiple of 2 pi, which results in an answer which is 1. Now, the summation n from 0 to n minus 1 has n terms. So n times when we add 1, the answer is capital N. Therefore, putting it back in the above equation, this is what we get. 1 by n square and n, you can cancel out 1n. The summation, you can see here, the second summation, we can change it because m is k minus l mod n. So we shall replace that m. And when you replace that m will change to l in the summation as well. Therefore, the summation L is equal to 0 to n minus 1 is a common for the first and second term. Therefore, we can express it as summation L from 0 to n minus 1. First term is as it is, x1 of L. Second term becomes x2 of k minus L mod n. And this equation we know is that of circular convolution. Therefore, we can call it as circular convolution between x1 of k and x2 of k. Hence the proof. Property number 8 of DFT is called as symmetry property of a complex valued sequence. Here, if x of n has DFT x of k, then we want to find what is the DFT of conjugate of n. So the star here represents complex conjugate. Here we believe that the input x of n is complex. So there exists its conjugate, which is x conjugate of n. Now this property tells us that in the frequency domain, we get x conjugate of n minus k. In other words, it is x conjugate of minus k mod n. So here we can see some elements of the time reversal property, but the additional part here is the conjugate. Alternatively, we can write it as x conjugate of minus n mod n has a DFT x conjugate of k. So if you have an input with minus n, here we get a plus. So this is called as symmetry property of a complex valued sequence. Let us just prove this property. Again, we start with the definition of the DFT. In this definition, let us take complex conjugate on both sides of the equation. Now, since x of k is complex, there exists its conjugate, which is x conjugate of k. On the right hand side, the input x of n could be complex and there could be a conjugate called as x conjugate of n. Wn to the power of kn we know is a complex exponent. Its conjugate is obtained by changing the sign of j. So Wn is e power of minus j2 pi by n. Its conjugate should have a plus. So please note we have changed the sign here to represent that. So Wn to the power of kn has a conjugate Wn to the power of minus kn. In the next part, let us replace the k with n minus k. Let us replace the k with n minus k. Then x conjugate of n minus k is equal to the summation n between 0 to n minus 1 x conjugate of n into Wn to the power of minus capital N minus k mod n. So what do we notice here? Since we wanted to prove that the DFT of x conjugate of n is x conjugate of n minus k, so we wanted to introduce this particular term. This is possible by replacing k with n minus k. Therefore, now we have the twiddle factor which can be split again into two terms, Wn to the power of minus n into n, Wn to the power of kn. and we know Wn to the power of minus n times n. The answer here again is 1. Therefore, the result we have is summation n between 0 to n minus 1 x conjugate of n into Wn to the power of kn. Now this equation once again resembles that of the DFT, with the difference that in place of x of n we have x conjugate of n. Hence it can be treated as the DFT of x conjugate of n. Other words, DFT of x conjugate of n is x conjugate of n minus k, or alternatively x conjugate of n has a DFT x conjugate of n minus k. Hence the proof. Property number 9 is called as symmetry property of real valued sequence. Here the input x of n is considered to be real. For real inputs, the DFT exhibits a symmetry, that is, x of k will be equal to x conjugate of n minus k. So this is what we need to prove. Let us start with the definition of DFT. Then, taking complex conjugate on both sides, now we know LHS becomes x conjugate of k because output may be complex, and on the RHS we can write x conjugate of n into Wn to the power of minus kn, which is the conjugate of Wn to the power of kn. Since we are aware that the input sequence is real, therefore x conjugate of n should be same as x of n. Then the equation now becomes simply summation n from 0 to n minus 1 x of n into Wn to the power of minus k. Therefore, this equation, in order for it to look like what we have here, that is, we have to have a term with n minus k, we shall introduce an extra term called as Wn raised to capital N into n, which is possible because we know that its value is equal to 1. So multiplying by 1 will not change the value. So we introduce this term. Now we combine the two exponents and you get the value Wn to the power of n times n minus k. Now if you compare this with the regular DFT equation, we notice the difference that in place of k we have n minus k. Hence this can be called as x of n minus k. Therefore, x conjugate of k is same as x of n minus k. Alternatively, we can take conjugate on both sides to get x of k equals x conjugate of n minus k. Hence, we have proved this property, and this is a very useful property. So this property tells us that provided that the input is real, the sequence will exhibit a peculiar symmetry. If you leave out the first point, the origin, the remaining points are exhibiting conjugate symmetry. The rest of the points will be exhibiting conjugate symmetry. The next property is called as circular correlation. Correlation is a sort of comparison between two sequences. Here we perform the operation circularly. If you have complex valued sequence called as x1 of n and y of n with the respective DFTs x of k and y of k, then the correlation between x and y is indicated symbolically as rxy tilde of L, whose DFT is capital Rxy tilde of k, which is equal to x of k into y conjugate of k according to this particular property. So we see that we multiply the DFT of the two, the second one happens to be conjugated. So this is something like the circular convolution that we have studied. Now in this Rxy tilde of L is the circular cross correlation sequence, which is defined by, let's take a look at the expression. Rxy tilde of L is equal to summation n between 0 to n minus 1 x of n into y conjugate of n minus L mod n. This expression is very much similar to the circular convolution. Minor changes are there. We have used L to represent a term which is called as lag. Lag represents the shift or the delay. At these lag points, we are calculating the correlation coefficient. If we observe here, the sign of n, the index for x and the index for y is same. This tells us, unlike circular convolution, we do not reflect the sequence. Rather, that n minus L indicates the shift. So there is no reflection part. The sign of n is same in both, but we do shift it by the lag, that is L. The second term is conjugated. So these are the primary differences between correlation and circular convolution. The conjugate and the absence of the negative sign here. Rather, we shift by a quantity called as L. Now, you have to remember this expression. Let's develop the proof. We can write Rxy tilde of L. Rxy of L can be treated as the circular convolution between x of n with y conjugate of minus n. As we had described, the difference was the second term is being conjugated and the absence of the step which is called as reflection or folding. So to compensate for that effect, if we convolve x of n with y conjugate of minus n, then it will become a correlation. Therefore, we can express Rxy tilde of L is equal to x of L convolved with y conjugate of minus L. Taking DFT on both sides, DFT of Rxy tilde of L is equal to DFT of x of L convolved with y conjugate of minus L. This DFT is expressed as Rxy tilde of k. Now we are aware from the property, we have learned from the property convolution that it becomes a multiplication of the respective DFTs. And the DFT of x of L is x of k. The DFT of y conjugate of minus L is y conjugate of k. This is using the properties, namely circular convolution and complex conjugate properties. So both these properties are coming into picture here to arrive at this particular result. Now let's talk about a special case. Suppose the two inputs x of n and y of n are the same, or they are said to be equal. So y of n is same as x of n. Then it is called as Rxy tilde of L. This is described as an autocorrelation. And its DFT becomes Rxx cap of k, which should be same as x of k magnitude square, because it becomes a multiplication of x of k with x conjugate of k. This is same as taking the magnitude of x of k the whole square. So this is the result that we obtained from the correlation property. Property number 11 is called as Parseval's theorem. For a complex valued sequence x of n and y of n with respective DFTs x of k and y of k, Parseval's theorem states that summation n between 0 to n minus 1 x of n into y conjugate of n. So this is the time domain. So in the time domain, we are multiplying input x of n with conjugate of y of n and finding the sum. This is equal to 1 by n times summation k between 0 to n minus 1 x of k into y conjugate of k. You observe in the RHS, we are considering the DFTs and we are performing the same action as in the LHS. Additionally, we are multiplying with 1 by n. To prove this, we have to rely on circular cross correlation of two sequences. As we have learned, Rxy tilde of L is equal to summation n between 0 to n minus 1 x of n y conjugate of n minus L mod n. Taking the value of L equals to 0, the equation reduces to Rxy tilde of 0 at the origin. This is origin, value 0. This is equal to summation n between 0 to n minus 1 x of n y conjugate of n. Call this equation as A. Now, we are aware that IDFT of Rxy tilde of k is Rxy tilde of L. And Rxy tilde of L from the definition of IDFT could be written as 1 by n times summation k between 0 to n minus 1 Rxy tilde of k, which is the input, and from the IDFT equation, we had Rxy tilde of L is equal to 1 by n times summation k from 0 to n minus 1. The input is Rxy tilde of k for the IDFT. And as you know, in the formula, we have e power of j2 pi by n k L. See, because the index that we chose here is L and not n. That's why we use L. And this Rxy tilde of k can be replaced with x of k into y conjugate of k because of the circular correlation property. And here also we shall consider the lag L is equal to 0 or the origin, and the result is Rxy tilde of 0 equals to 1 by n times summation k from 0 to n minus 1 x of k into y conjugate of k. Now, using both equation A and B, which stand for the same term, when you equate it, equating the RHS of both equations, the result we get is what is expected. So this is the result, summation n from 0 to n minus 1 x of n into y conjugate of n is same as 1 by n times summation k from 0 to n minus 1 x of k into y conjugate of k. Further, as a special case, if x of n is same as y of n, then the LHS is the expression for the energy of the signal, that is summation n between 0 to n minus 1 x of n, and x conjugate of n is x of n magnitude square, and on the RHS we have 1 by n summation k 0 to n minus 1 x of k magnitude square. So this is said to be the energy in a finite duration sequence x of n, both in terms of the time domain as well as the frequency component x of k. So this equation can be used to calculate energy of the signal both in time as well as frequency, and simple example can be used to test the results whether it is true or not.
Thank you all.